So a very good afternoon to everyone. So mm, and also welcome to the week 8's tutorial section of the principle of casting technology. So I am Rohit Gehlot and I will be taking the tutorial for this. So as discussed in the last week, this you have students have requested to uh, do some problems regarding the iron carbon diagram and explanation regarding some other stuff. So I will be covering those in this tutorial. So let's start with the uh, explanation or the iron carbon diagram. So as the theory has already been covered, so I will be just briefly discussing to recapitulate the concept and all. So as you can see, like in the leftmost figure, the iron carbon diagram and regarding the other terminologies I have given. So firstly I will be explaining the different terminology. So if I talk about the different terminology, so let's start with the perlite. So it is formed by the decomposition of the austenite at around 723 degrees centigrade. So if it so if I write it here so it is formed by the uh, decomposition of austenite around 723 degrees centigrade, and like the decomposition of further the decomposition of the austenite, it leads to the formation of a eutectoid mixture of around 88% ferrite and 12% cementite, which is which is called as pearlite. So it is 88% ferrite, and then 12% is cementite. So if you talk about the structure, then it constitute of alternate layers of ferrite and cementite, and it also comprise around 0.8% of carbon. So if I write it here so I will write ferrite as F and cementite as C. Okay, so alternate ML or of ferrite and cementite. Okay, and then for if we talk about uh, hardness and softness, so ferrite is soft and ductile, and perlite is of if we talk about and cementite is comparatively not soft and ductile. So as the majority is ferrite, so So if you talk about the perlite, so the perlite is of kind of like medium hardness and it imparts mechanical strength to the steel. Okay, and then if you talk about the second thing like ferrite, so it is like the alpha iron and the solid solution of so it is like a solid solution of carbon in alpha iron. Okay, now the carbon atoms like are dissolved interstitially in the BCC structure here, and the maximum solubility of carbon is like around 0.025% at around 720 degrees centigrade, and it is also like very soft and highly magnetic. Okay, so this is like soft and magnetic. And this is like a solid solution of carbon in alpha iron. Okay, then if you talk about also the different phases, like so there are like delta ferrite also. So this is a solid solution of carbon in iron. This is a solid solution of carbon in iron, and also the maximum concentration of like carbon is around 0.09% here, at around like 1490 degrees centigrade. Okay, then if we talk about the austenite, so this is an interstitial solid solution of carbon in delta iron. Carbon in, actually it is not delta, it is gamma iron. Okay, so it is an interstitial solid solution of carbon in gamma iron, and it has like FCC structure. And then it does not exist like below less than like 723 degrees centigrade does not exist. Okay, then if we talk about the cementite, so cementite is iron carbide, like it is basically a iron carbide intermetallic compound, and it is having a fixed composition like Fe3C. And cementite is like a hard and brittle substance, like, and it also which influences the properties of steel and carbon iron. Okay, so if we see the diagram, so like the alloy which contains around 0.51, and alloy is around contains around here like 0.51% of carbon, start solidification with the formation of crystals of delta ferrite. Okay, and then the carbon content in the delta ferrite like increases up to 0.09% in core solidification and at around like 1492 degrees centigrade remaining liquid phase, and the delta ferrite perform the peritectoid form that transformation. So like So I think everyone knows like there are like generally eutectic transformation, eutectoid transformation, and peritectoid transformation, which are like highlighted here also. And I think like in the theory also it is covered like which transformation is from liquid to solid, solid to liquid. And the sum of the two like has already been like covered and everyone knows. I think if if you have any doubt, like please ask me. And like beside this, like if we talk about the so the like so the iron carbon like alloys like containing up to around 2% of carbon are called steels. 2.06% are called steels. Okay, like these are like cast iron and these are the steel. So less than around this particular composition, it is steel, and then above it, it is like termed as cast iron. It is 2.06. Okay, then and maximum around 6.67% is termed as like cast iron. Now in so in generally like only like these uh, hypoeutectoid alloys are used. Silicol and here like the carbon content is like 0.02 0.8%. So like these are also the good terminology like from which to which is what is called. Okay, then if you like move to the following question. Before following these questions, like I would like to like solve these two numericals like which are based on the iron carbon diagram, and specifically uh, on the one very simple like concept which is known as the Lever's rule. So I would request you all to please try to solve this and go through the question. So I will read the question for you. Like so, there is a steel sample with around 1.58% of carbon, which comprises and which comprises no other alloying elements present. Like it is slowly cooled from 1100 degrees centigrade to just below the eutectoid temperature, around 723 degrees centigrade. The part of the iron cementide phase diagram is shown in the figure. The ratio of the pro-eutectoid cementide content to the total cementide content in the microstructure that develops just below the eutectoid temperature phase. So please try to solve this. After that, like I will explain the concept. Okay then, so let's solve this problem. So firstly I'll reread. So there is a uh, so there is a steel sample with around 1.5% carbon, and there is no other alloying element present, which is slowly cooled from 1100 degrees centigrade to just below the eutector temperature. Okay, so we need to find out the ratio of the pro-eutectoid cementite content to the total cementite content in the microstructure that develops just before the eutectoid temperature. So firstly, if we draw the so there's the diagram is given. So here okay, so this point you see here, this is the eutectoid point. So this is the eutectoid point. Okay, and if here is it is the gamma phase here, then this is the alpha phase, and then if you say you give C0 phase, kind of yeah, it will be C0 phase, and then if it is say at C2 phase, here it is Fe3C is forming in the off. Okay, so if we okay, so if we simply do it by a Lever's rule. So this is your C0 concentration, this is your C alpha, and then this is your Cl. So here the at C alpha your concentration is 0.035, it is given. Sorry. So here your concentration is 0.025. Here it is C0 and here it is 0.8. Okay, so if you find a mass fraction of liquid weight. Okay, so if I write as so your the mass fraction of liquid weight so we can write it as C0 minus C alpha divided by Cl minus C alpha. So this is your liquid. Okay, and then similarly the mass fraction of solid weight of alpha, this can be written as Cl minus C0 will be divided by Cl minus C alpha. So this is the analyze how we can use the Lever's rule. So now if you find out the mass fraction of the pro-eutectoid cementite, so it can be suppose I say it's M1. Let's move to the new. Okay, so if we write it as so the mass fraction of third cementite. So it can be written as, so M1 is equal to, so this will be like this difference 1.5 minus 0.8 divided by total 6.7 minus 0.8. Okay, so I'll write it as like 1.5 minus 0.8 divided by 6.7 minus 0.8, which will come as 0.1186. Now if we calculate mass fraction of total cement, I'll write it as so M2, which can be given as, which can be given as like 1.5 minus 0.035 divided by 6.7 minus 0.035. Okay, I'll write it as 1.5 minus 0.035 divided by 6.7 minus 0.035. So it will come as around 0.2198. In the example, it is asked the ratio of these two. So M1 by M2 0.1186 divided by 0.2198, and this will come as 0.54. This is your answer. So please revisit the problem, and then we will discuss again this if there is any confusion is left. Okay. But then, so in generally, in this problem, we utilize the levers rule. So as it is given, we need to find out the ratio of the pro-eutectoid cementite content to the total cementite content in the microstructure. They develop just below the eutectoid temperature. Okay, so the eutectoid temperature we know here, the carbon percentage is 0.8% is given. Okay, now so we need to find out the develop just below the eutectoid, the ratio of the pro-eutectoid and cementite content to the total cementite content. Okay, so what we did, we find out the mass fraction like before and total cementite content. Okay, so as it can be seen, so we utilize the levers rule. So I explained here how the levers rules is applied for calculating the liquid as well as the solid fraction. And then here we calculated and here we calculated the mass fraction of pro-eutectoid cementite and the mass fraction of the total cementite. So let's do one more problem similar to this, which will help to explain more. So, okay. So here the binary phase diagram of metals P and Q is shown in the figure. So an alloy X, there is an alloy X containing 60% P and 40% Q by weight is cooled from liquid to solid. So here it is cooled. The fraction of solid and liquid in weight percentages 1250 respectively will be the fraction of weight. Okay, this will also be so this is a liquidus, this is your liquidus line, this is your liquid, and this is your solidus. Okay, so try to solve this, after that we'll do it. This is a simple problem. So here this is your liquidus, so below this you need to see this line, this point, then this point, and thirdly or this point. This line will be your this 3.3240 and then 68. These 3 points will be your lever line. So try to solve this. So if you see, so in the problem it is given there is an alloy comprises around 60% of P and 40% of Q, and we need to find the percentage of solid and liquid fraction at around 1250 from so we will do it from the Lever's rule. So we can write it as Ms is equal to My minus Ml divided by Ms minus Ml. Okay, so this will come as your My is around 40 minus Ml is 32. If we divide it by 68 minus 32. Okay, so this is your 68, this is your 32, and this is your 40. So this will come around 22.22. Now if we calculate for the liquid, so this can be written as so I'm not writing the formula directly, I'm writing, so it will come around 68 minus 40 divided by 68 minus 32. So this will come around 77.8%. So the fraction of the solid and liquid will be, the solid will be around 22.22%, while the liquid will be 77.8%. Okay, so we just applied the Lever's rule here, and to solve this, so try to go through it again, and then we'll move to the next problem. So I think the levers rule it's clear now. So here if we I draw again. So this was around 32. Here it was 40 and here it was 68. And then we apply the levers rule. And we solve this. Now if we move to the next problem, which is the number of phases present in an equilibrium at eutectic point. Is there anyone who would like to comment on this? So the number of phases present in an equilibrium at the eutectic point is. So I write here so the at the eutectoid point, sorry, at eutectic point. The number of phases which are in so there is one liquid and two solid phases are present. So total is three. So the correct option is four. But suppose if in exam it is asked what will be the degree of freedom. So then how we will calculate it? So we know that degree of freedom, it is written as like f plus p is equal to c plus 2, and if there is only one constant like which is pressure, it can be written as like f plus p is written as like c plus 1 at constant pressure. Okay, and now we know that the number of phases are 3, and then for a binary system number of components are 2. So it can be written as p plus f equals c plus 1. This can be written as 3 plus f is equal to c is 2 plus 1. The degree of freedom comes as 0. So it can also be commented as the degree of freedom reduces as the number of phases increases. So here the number is 3 and degree of freedom is 0. And also at triple point also degree of freedom is 0. So it is a two component system, can't have more than 4 phases in equilibrium. Okay. So again go through this, and if you have any doubt please let me know. Go through this problem again for 1 or 2 minutes, then we will move to the next problem. Okay, then so if we talk about talk more about this, what we have discussed, there are three important transformations. So there are three important transformation in iron carbon diagram. So let's discuss this in detail. There are so the first one is eutectoid reaction. So here at temperature, so it happens at around temperature of 723 degrees centigrade, and carbon content is around 0.8%. And second thing is that here the austenite, the gamma, it is a solid state. It is it is in equilibrium with ferrite, alpha iron, this carbide, which is Fe3C. So here one solid is in equilibrium into two, one solid converts into two solids. Okay. Now if we talk about the eutectic reaction. Here it happens at around temperature of 1130 degrees centigrade. And the carbon content, it is around 4.3%. Here one liquid converts into an austenite, and cementite phase. So here one liquid is converting into two solid phase, and then the third reaction is peritectic reaction. So it happens around 1498 degrees centigrade. The carbon content is around 0.09% carbon. And here the delta iron, it reacts with liquid iron. And is in equilibrium with the austenite. So here one liquid and one solid converts into another solid. Okay. And also it was clear from here at around less than 0.84% carbon steel or hypereutectoid is perlite plus ferrite, and then more than, yeah, I will write it more again. So at around less than 0.84% carbon, so steel or hypoeutectoid. It is like pearlite plus ferrite. And at more than like 0.84% of carbon,